All right, everyone, welcome back to Computer Science 354, Machine Organization and Programming. My name is Mike, and this is the third part of Week 3's lectures. We're going to talk about structs. So a structure in C is basically a composite data type. If you're familiar with classes in Java or C++, those are object-oriented programming languages, and a class in those languages are going to have both data and functions that go with them. We use classes to create instances of objects of that type. Those objects will have, data and functions that manipulate those pieces of data. Now, C is not an object-oriented programming language, so we don't have classes or objects in the same sense. Structures are just going to be, they're data structures where I've got the ability to put a whole bunch of different, maybe even unrelated types of data in the same structure. So in this case, I'm just going to go through an example, and hopefully it makes a lot of sense. I'm going to be creating a student struct. The student will have both a name and an ID number. So I wanted two different types of data, and I wanted to keep it as simple as possible, so we're only using two types. And then I'm going to go ahead, create an instance of that struct. Oh, here we go. This is what it's going to look like. I'll go ahead and put this in actual code and walk through it. But the name of the student is going to be a string. So we'll have a character pointer to the string data. And we'll also have the ID number just as an integer. And I'll walk through that in actual real code. And then I'm going to be creating an instance of that struct, which, and I'll assign the values, the name Mike and my student ID number. Please don't take advantage of my student ID number. Don't use it to check out books from the library. It's top secret. All right, I'm starting a brand new demo file. I've got my basic hello world structure so that it'll print something. I can see that it's working when I do some testing. And the first thing I'm going to do in this lecture is create a struct. The keyword to create a struct is struct, and I need to give it the name of my struct. So it's going to be struct student. Then everything, all of the data that we're encapsulating in this composite data structure is going to be contained within two curly braces, and it ends with a semicolon. So whenever I write a struct, I always fill this in, and then I just break that part and then put in my data. So in this case, we're going to be having a name and an ID number. The name is going to be a character pointer, like that. I forgot my semicolon. And the ID will be an int, just like that. There we go. That's all there is to creating a struct. Then let me just compile this and make sure I didn't make any mistakes. So we'll save that. There we go. We're again compiling with the 32-bit option so that the address space is a little smaller when we look at how it's storing these structs. All the warnings, but it looks like it worked. Okay, so the next thing I want to do is give it some data and print that out just to make sure that it's really working. Just the definition. So this is the definition of a struct. That much didn't give me any compiler errors. So in order to declare an instance of a struct, I need the name struct. And now I've created this data type. And here's the name of it, struct student. And I'm going to create this first student. It's going to be, let's call him student. We use lowercase to differentiate that between the name of the struct and who we're creating. And then in order to fill in these data values up here, the name and the ID, we will go ahead and use dot notation to access the data members. So student.name, I can give that the name Mike. And then the student ID, we'll go ahead and give that, oh, I missed the one, my student ID number. And from there, we can go ahead and print these things out. So in order to do that, we'll just print out name, and this is going to be a string, so %s, student.name, and printf ID. That's an integer, so we print it out as decimal value, student.id. Oh, and I want to put some new lines in right there, and another new line. I'm not using Vim. All right, save it. So compile this and print it out. There we go. Compiles no problem. And we'll print it out. There it is. So looks like the struct is working. Next thing I want to do is print out the addresses where all of these, where the two data members and the struct are stored in memory. So I'm just going to go ahead and add this right here. Name student at address, and then an address is going to be %p. Same deal with the ID number. So print out the memory address for that, and then I need to add those items. So this is going to be student.name, but I need the ampersand, there we go, for the address of, and missed again, student ID, address of student ID. And then one more final thing, I'm going to put it up at the top here, printf, I want to get the actual student address of, that's %p because we're getting address of student. So let's take a look at what these give us. Save this, compile, and run. Oh, I forgot a new line. Unacceptable. All right. There we go. So we're looking at the bottom right here at these 3 lines. Get those highlighted. First, the address of the student. This is the overall struct. Is found at, looks like FF18. And then we've got 2 pieces of data. A pointer to a character, string FF18. So the address of the struct is actually the same as the first piece of data. So it works just like the arrays did. The address of an array was the first piece of data in the array, element 0. For a struct, the address of the struct is the address of the very first piece of data. And then we've got the second piece of data at actually this is 4 bytes higher. Now Mike as a string is going to have 4 letters and 1 more character for that null terminal. So this would actually be a 5-byte piece of data. This is actually just a pointer though. In fact, right here, that char star means that this is a pointer, and all pointers depend on the address space that we're looking at, and it's a 32-bit address space, so 4 bytes is how much space they take up. One second, let me see if I can figure out to print out where the address of the actual word Mike is. One second, let me put that code in. Alright, I actually got this right on my very first try, but my confidence was obviously pretty low from the tone of my voice. But here's all I had to do right here, print out address of string Mike. That's actually what's stored in this pointer right here, the address of this array. So all I needed to do was give printf the command to print it out as it's a pointer, give me that address where it's pointing. And here, when I was printing out the name, in fact here, check this out, student.name is exactly the same thing that I printed out here. The difference is I told it this is a string. So what printf is going to do is follow that pointer and print out the characters of the string like we'd expect it to do normally. Normally we wouldn't want this address during typical usage of a string. But in this case, I want to highlight one little quick thing right here. Let me pull this back up. These are the new lines. I've got address of student at FF18, the first piece of data, the name at FF18. That's where the pointer is stored. And this pointer, the character pointer, actually contains this address, this 0040, 5061. And this is much larger addresses than where the data for the word Mike is. Now, if you remember back 2 lectures ago, I had a picture of the entire address space. Let me pull that up in a second. But it had the actually, let me pull that up right now. Let's see, that was a PowerPoint right there, and it was way at the beginning. Yeah, right here. This is the picture I'm talking about. So in the address space, for the entire code that's available, address 0 is reserved. We use that to assign to pointers to indicate that they've not yet been assigned. Then we've got a block of memory reserved for the code. There's not that much here. And then this is the piece right here. This next section is reserved for all of the string literals and global variables. And let's see here, it's known as the text section. When we go back to this, we can see that this is actually a string literal, and it's being stored in that block at much higher memory addresses than the heap, and then all of the stack is going to be at the very bottommost addresses. So we would expect, where's PowerShell, the address where I'm storing Mike to be a smaller number or closer to the top of the address space than the stuff that's on the stack, these three pieces of data. All right, next up, what I'd like to do is talk about the connection between a struct and the memory model. And but there's only two numbers here. I mean, drawing a picture is going to have very few things in it. Actually, let me go ahead and do that anyway. We'll just build this up. Let me go draw that picture and I'll be right back. All right, so I've got my picture put together here. This is all the same from the previous slide. Here's the screenshot from PowerShell. And then I've got two places in the memory. This is that text data section at address 0040560. Oh, that's not right. Hold on. 5061. Give me 1 second here. I'll get this edited. Pop that down. Like that back. There we go. That looks good. Okay. Yeah, at address 405061, I've got the letter M. It's the first character in my string. Note, this is now at an odd number. It's not a multiple of, 048C that we saw with all these integers. Typically what we'll see is that the starting value for any particular data structure is divisible evenly by the number of bytes in that data structure. So an int has 4 bytes. The starting addresses are going to be divisible by 4. Character data has 1 byte, so it's going to be divisible by 1, or anything is possible. Something like a double is going to have 8 bytes with it. The starting addresses for doubles will be divisible by 8 bytes. And we'll see that like the beginning of stack frames and the amount of data reserved for local variables, frequently that will be straight up divisible by the largest possible thing that we might have. So if the largest possible data type is a double, we'll frequently see that those beginnings of stack frames are divisible by 8 bytes, or whatever the largest size is. All right, little aside there as to why this starts on a 1. All right, so then for the data, what's actually stored in these things, this first address right here that's got something, the 61FF18, this is the address where the struct is stored. It's also the address of the first piece of data. That piece of data is a character pointer right here, char star. And so it contains an address, and that address is the 00405061. That same, it's a pointer. Let me grab an arrow. 1 sec. Here we go. Here's an arrow. You can get that flipped around, pointed at the right spot. There we go. That looks good. It's a pointer to that address. And then the other piece of data that we have in the struct is the ID number. So it looks like this particular compiler has chosen to put the pieces of data in the struct in this order. It's up to the compiler how they're going to order things, and that's just what this one happens to look like. Typically, though, they will be in this order. I don't remember ever seeing them not in that order. I might have to do some more experimenting, see if I can trick it into changing that. It might not. Okay, all right. Enough rambling. Mike, the next thing I'm going to do is I want to create a function that's actually going to print this out, and we'll compare what happens to main to when we pass a structure to a function. Let me go pop back over to, here we go, my editor. And what I'm going to do is print out this same struct with a function call. So I'll print struct, let's call it student. Student. This is going to take the name of a student structure. Student is my name, and we'll just print it out. All right, I can see right now it's a void function. I need to put it after my definition of the struct. It needs to come after that because we need to see this first, and then we'll have print student. It's a void function, no return value. It takes a struct student type, just like that, and we'll call this S inside the function. There's my prototype. Let me go ahead and now write the function definition down here, get it out of the way. So that means I get rid of the semicolon, we add some brackets, and I'm going to be printing out all of this good stuff right here. So print the address of, in this case, I'm going to just change this. It's going to be address of S. S, 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 S. S, there we go. Got all the word students changed to S, because that's what I'm calling it inside of here. And clean that up a bit. All right, let me go find out what all the mistakes I made. So pop, save it, pop back over here, compile. No mistakes. All right, let's run this. Oh, I forgot a new line right there. All right, let's get that fixed. Where was that one? Right here. I'm going to put in 2 actually, and leave 1 right there. So that second one will leave a blank line between the 2 print statements. There we go. Okay, so this first block, this is the one from the function in main, printing out the student, and this is the one from the function call, the print student function call. All right, so none of these look like they've changed. I still have the address of the student at FF18. First piece of data, FF18, 1C is 4 bytes after that. Address of this string, 5061. Yeah, that hasn't changed. I've got my other monitor has that slide opened up. So if you've got PowerPoint and you're looking at the slides, you can see they haven't changed. All right, next up, when we actually pass this data structure to the function, I can see that I've created a new student piece of data structure right there. It's a struct student of named S, of type struct student. When we pass that, everything is called by value, so we're making copies. So this is a new struct at this location, FF00. It doesn't appear up here. The first piece of data, the address of Mike, got copied into FF00 right there, which is the same. The name of the struct goes at the, is a lot like a pointer to the first piece of data. The 1, 2, 3, 4, 5, 6 got copied into this address, the next one, FF04. And what we see is that this name is a pointer, and it needs to point to the very same string that this one does. It's called by value. So the ID number 1, 2, 3, 4, 5, 6 got copied. The address in that pointer got copied, and it should be the same address as right here. So that's pretty good. Let me go ahead and copy this into my memory model picture and just show you where everything is all laid out now. One sec, let me go build that slide. Be right back. All right, got this put together. Here's the screenshot from the previous, the PowerPoint, or no, not PowerPoint, the program output. I can see that none of this original data from what was printed in main has changed. All the addresses are still the same. So this number here and this number right here, this is my original student struct in main. In the text section, I still have the string Mike, terminated by that null terminal character, still there at the same address, so that's all good. Now, when I called the function, everything is passed by value, so we've just made copies. It's created a new struct object, and remember the stack is growing towards smaller addresses as it, from that very first picture, I've got the main at the very bottom of and then the next stack frame, the print whatever, goes slightly above that. So these should be at lower addresses, but probably, still in the stack. They should be pretty close to these guys. And in fact, there's only a few empty, well, they're not empty, but a few bytes in between them. This is going to be reserved for things like the return address, the base pointer, some padding, things like that. And now we can see that what we've got here is the very first piece of data at my struct. So this 61FF00 address is the name of the S struct inside my function. It's the parameter of the function. What we've done is we've copied in this address, 00405061, got copied into the first piece of data, which is located at the same location. The S struct is the same location as the S.name when I start looking at addresses for structs. And then that ID number is the very next, 4 bytes down, because this is a pointer, it takes up 4 bytes. My ID number is an integer, will take up 4 bytes also. But we've just made a copy of that. All right, so that's how this works if I use call by value with the struct. Now, this is not super efficient. I've gone ahead and made a copy of both pieces of data. All right, so let's face it, it's 8 bytes. That wasn't a big deal. But suppose I were looking at something like genetic data, and I had a genome that I wanted to pass to a function to print out, or to print out a piece of it or something. This is very inefficient to copy large pieces of data. So a better way to do this would actually be to pass a pointer to this student object. So let me go ahead and write a function that works essentially the same way. In fact, I'm just going to go ahead and write it right here. Void print student with pointer. This will take data type struct student, but now it's a pointer to that student. We'll need some of these guys, and then we'll just print this out. I'm just going to copy this. It gives me a really useful error message when I do it like this. This doesn't work. I no longer have a struct student. This is a pointer to a struct student, so this is going to fail. But I want to show you that error message. And I also need a prototype up at the top. So let me go ahead and grab that. And down needs a semicolon. And then we're also going to need to call this function. I'll just speed that up a little bit. And let's see, let's put another blank line in right there so they're separated a little bit. Another blank line right there. All right. Looking good. Next up, compile. Really super useful error message. I want to take a look at the top one first. So this is a incompatible type for argument 1. I didn't give it, I gave it the student, not a pointer to the student. So a pointer needs to take an address. That problem came from right here. So I'm trying to copy this student data into what's supposed to be a pointer. So instead, pointers take the address of. So there we go. That error message again was incompatible type. It says expected struct student pointer, but it's struct student. So that just means that I needed the address of. All right, next up, I'm going to save that, compile it again, and now I should get some different error messages. So here is the new top error message. S is a pointer, then I mean to use the dash greater than, or the arrow. I'm just going to call that the arrow from now on, instead of that dot. So this is really useful. It tells me I need to use that arrow instead of the dot. And that's going to go anywhere I have dot in the pointer version. So here's the problem. When I've got something like this, and I try and dereference it or use it, instead of this, what I'd really like is to dereference the pointer and then grab the ID. Now the problem is this dot is a really high precedence. And that means it's going to take S, which is a pointer, and it doesn't have any of these data members. It's a pointer. It's 4 bytes with an address in it. It does not have a dot ID. And in fact, let me go ahead and we'll do this very first instance right there. I want to show you the error message when I do put in the star. But because this is so high precedence, this is still going to give me a problem. But it's a different error message. Let's go ahead and compile that. Let's see. Error S is a pointer. Did I mean to use arrow? Still, it's the same. Oh, it's the same error message, and that's because it's trying to do this first. S.name, and it's telling me S is a pointer. It doesn't have a .name data member, and suggests that I use that arrow. So another way to do this is to say, well, that star operator is low precedence. We can use parentheses to make this higher precedence. So this should now work, and I should get another error for the next. I believe this one. Let's find out. I didn't save it. There we go. Compile that. There we go. So let's see here. Print student. Right here, name. Yep, it's now giving me an error message for this one because this s.name also does not have the s is a pointer here also. But this one now is no longer giving me the error message. So I can either do this or I can use these arrows. So there's an arrow, and anywhere I have an S in this, because it's a pointer, I will need that arrow. There we go. And the arrow is just shorthand for doing this. That's all it means. And let's face it, as you're going through, this is something the programmers who are developing C wanted to have, because it's really hard to remember to type parenthesis star S parenthesis dot every time I need to use the dot. It's much easier to type S and then think, oh yeah, it's a pointer, after you've typed it, and not have to backspace and replace that. So they instituted this arrow operator. Actually, I don't know that that's the reason. The arrow is really convenient. I really enjoy using it rather than this sort of syntax. All right, I think I got all the places. Save that. Let's go run this. Compile first, then run it. There we go. Looking good. This first block is the data getting printed out in main. Addresses have not changed. This second block, we've called the function, All right. This is the original, the very first print student function. So we're making a copy. The data here is at ff00. That data is at ff0. That's the new struct, and we've made a copy of both of these data members. Okay, and the location of Mike still has not changed. Now, when we did the pointer version, we still created a pointer address of s. S is now a pointer here. It's still given the same address because we've popped off the stack frame for this print function, and now we're generating the stack frame for this print function. Now, because this is a pointer, it's actually pointing to this data right up here, the stuff in main. So these addresses should be exactly the same as the addresses in main. I only had to copy 4 bytes for a pointer to this location right up here in main. And same thing down here, this is the same address as that one. So I had to copy 4 bytes instead of the entirety of, well, it's only 8 bytes here, so not a huge deal, but I didn't have to copy the whole thing. A mere 4 bytes of data got me what I wanted. All right, just thought I'd put this into a picture too to try and make it a little more clear what's really going on. And it gives me a second chance to talk about it. So if you didn't get it the first time, maybe this will make sense. So this is what happens when we call print student with pointer. In the previous slide, right here, this one, I called print student and it made a copy. So I had 2 pieces of data that I copied. The first one was the character pointer to my address. All right, let me actually add another arrow and get this in the right spot. Something like that. So it copied that pointer, and then we had to copy the data also. Now, when we called the print student with pointer function, all we did was create a pointer to the data that was already in main. So this now, instead of getting, basically this is the address of my struct 0061ff1c. Oh, that's the wrong address. It's the first one, 18. There we go. My bad. So we're getting a pointer to this very first piece, this address right here. And then from there, that I can use that to access both of these pieces of data using that arrow operator. All right, I just checked my notes, and there is one more thing that I do want to talk about today. And that's here, the idea that I have to type struct student, anywhere I wanted this, struct student. I keep having to type the word struct over and over and over again. C gives me a way to rename my data types. So this is me creating a brand new custom data type that holds 2 pieces of data. I'm going to leave that right there. But for the moment, while I'm exploring, I'm going to comment this piece out and then show you some alternatives. So the first one is, well, here, let me do it this way. We'll break it down a little more. Before I do that, there's a function typedef. What this is going to let me do is rename data types. So in this case, my data type that I just created is struct student. Just like that. I can rename this to anything I want. In this case, let's call it just student. Now, I did this because this is so common, and it can be confusing because I've got the word student twice in a row right there. But this much is the data type that I've just created right here in the line above it. And this is what I really want to be calling this. Now, this code will compile no problem because I can use the original name. It didn't go away, it's still there. But I can also now use my new name, which is just that much, just student. So I can go ahead and delete this, and it should still work just fine. Let me go ahead, compile, demo this. I'm not going to run, I'm just going to compile it and show you that there's no errors. So C was totally willing to accept my new renamed student data structure. This is really common using the same name twice. So I'm going to go ahead and leave it, but there's no reason you couldn't shorten this up to something, we'll just call it Stu for student. And then I can rename it this one Stu, and this should also work. It's just I've renamed it something different. So if that makes more sense, go ahead and think about it that way. There we go. Spell that right. Whoops. Undo that. That. Okay, now it's back to the way it was before. Now I've got some other options too. I can actually, let me comment this out for a moment. And we'll comment this part out. And I'm going to copy and paste my new my original definition. I'm going to put it all in one line for a second. There we go. So now I'm just declaring a struct student. I've got all my data in one line. C does not care about spacing like Python does or indentation. It does not matter at all. What I can do is say this is my definition for a student in a struct student. Instead of just this much, I can just replace that with this. So in this case, I can say I'm going to just copy my type def line, and now I'm going to take my definition for the struct student, the entire thing right there, and just put it in right here. Copy and paste that. I don't need the semicolon right there because I'm creating a type def of a struct that I'm naming student. All right, and this should be enough. I still have my student here without the struct. I've just named this student. So this should also still compile. Let me save that, make sure that I really don't have any typos. I do. Oh, redefinition. So somewhere I have got it twice. Yep, right there. I need to do that. So here I was declaring struct student, and here I'm also declaring it again. I think that's the problem. Let me make sure. Yep, there we go. I had it twice. All right, so now this is basically this line of code right here takes care of the creation of an entire struct. I'm going to do one more little thing. Because I've got the name here twice, I don't actually really need to give it a name at all right here. I can get rid of that student. I don't want to redefine it. I only want one of these right here. This, I believe, is the absolute shortest, most concise way to create a struct with a particular name and not have to worry about having to type struct over and over again. Let me make sure I didn't have any typos and that this works by compiling it. Do have a problem. I have a typo somewhere. I found my mistake. So this was actually pretty straightforward. When I removed the word student right here, okay, I'm creating an anonymous struct that told the compiler that I no longer have this. It's now anonymous, and I'm just calling student. And then all over my code, I was calling struct student. Okay, instead of student. I no longer have struct student available like I did before by putting the name in right there. Instead, what I need is to get rid of the word struct everywhere except right there. So if I delete that one, let's see, where else have I got one? Here's a struct right there. I need to delete that one. Then down here in my function call, in my other function call, did I get them all? Student, I believe so. So now this should compile. And there it is. Compiles just fine. Let me go ahead and run this. We can see it's producing the exact same output as before. Yep, looks like FF18, FF1C, same output. So anyway, this type def idea, it's a way to create an alias. It's a way to take the name of a type usually used with structures. In a second, I'll show you another way I've seen it used, but it's a way to just rename something so I don't have to type the word struct over and over and over again. And I can also just, well, here's another way that I've seen this used. I may have type def floating point numbers. So what I'm going to do is rename float to t. It's actually creating a second name, t for type of numbers, I suppose. And now if I do all of my variable declaration using t instead of float, floating point number computation is at least a little bit faster than using double precision numbers. It takes up less memory. But if I want more precision, I can change my entire code to use double precision numbers, slow it down, get more accuracy by just changing one word right here. But then in my main function, I'll have, t caps lock t of x equals 3.0, t of y equals 4.0, t of z equals x plus y. So there I've got all of these are right now double precision numbers, type double. And if I want to switch them to floating point numbers, all I need to do is change what my alias refers to, what my type def refers to. Okay, so I'm going to go ahead. I'm going to leave that in. It's an example. I'm going to return all of my comments so that I'm using the most basic original version. I'm going to keep this one only right there. We'll keep these commented out, and I'm going to put the word struct back in all over the code, like this, like that. So when you guys download this code, it'll start out looking like it's got everything it needs to operate with the original definition. And then you can go ahead and play with this, delete it yourself, make sure it all still works. And I think I got everywhere. Nope, there's one more. Let me compile this and run it. Make sure the code that I give you guys works. Got one more. Oh, unused variable. All right. Not a big deal. I'm going to leave that warning in there. All right, that's going to do it for me. That's everything I wanted about structs, I believe. There's... no, I think that's it. All right. Anyway, have a great day. Let me go edit this video. I'll get it put up on YouTube, and I'll send everyone an email. Have a great day.